This is lecture 8 in signals and systems. Right, in this lecture we are going to discuss what are the properties of impulse function and what are the different types of discrete time signals. In lecture 6 and 7 we have discussed about the periodic signals, non-periodic signals, power and energy signals, even and odd signals, what is the sync function, signal functions, and in lecture 7 I solved some problems on these different types of signals, how to find even and odd components of given signal, how to find the periodic of a given signal, now finding that it is a periodic or non-periodic, now how to find power or what is the power signal, how can we define a power signal, how can we define energy signals, so that you can see in lecture 6 and 7. Now in this lecture we're going to see properties of the impulse functions. So if you see the previous question papers, you will see 4 or 5 questions coming from the properties of impulse function. Next we will see the discrete time signals. Now we know what is the impulse function, delta t equal to 0 when t not equal to 0. When t equal to 0, the amplitude is infinity, or we can say the area minus infinity to infinity, delta t dt is equal to 1. So this is the del function normal properties, right? So that it is represented by like this. This is del t and this is t. Now we are going to see some properties of this impulse function. So what are the different types of properties? The first property is the sampling property. That is, if I multiply with x of t into delta t, we will get the output as x of 0. This is the first one. The second one is, if x of t is delta t minus t naught, then this will become delta of t naught. If we compare this and this, here t minus t naught is nothing but 0, so that is x of 0. What is this meaning is, if I take some x of t, something like this, 0 to 1 and 2 something 3 dt, this is x of t, right? We know the del function is here, delta of t, area is unity. If I multiply these two, wherever the impulse is there, that will be amplified, or amplitude will get at the output. So the resultant, if I multiply these two, I will get an impulse at 0 only, right? Similarly, if I delta t minus 1, suppose it is like this, at 1 we are getting the impulse function. Now if I multiply these two, the resultant will be at t equal to 1. What is this value? Amplitude. Suppose this is 1, we will get amplitude is as 1, right? Here is a area, but here it is an amplitude. So whenever if I multiply with the del function, we will get the sample of the input signal, or x of t at t equal to t naught. If t naught equal to 0, x of 0, t equal to 1, x of 1, etc. These are the two very important properties. Next, one more property of the scaling property, that is third. If delta of at is there, so this will be equal by 1 by mod a delta t, right? So this is a very important property. If I scale the del function, it will become like this. So the time will not be changed, but only the amplitude will change. That means, suppose this is delta t, area is 1. If delta 2t we need to find, what is the value we should get? Here we will get 1 by 2 and delta t. So this is 1 by 2 delta of t, right? So the time is as it is will be there. There is no time scaling, but amplitude will be scaled down. So that is the del function, right? Now it's simple to prove this one. So what is the proof? We know that minus infinity to infinity, delta t dt is equal to 1, right? Now So how if minus infinity to infinity, if delta t is replaced by delta of at dt, right? So how to find this one? This is so it should not be at, so we need to assume at is equal to some tau. What is dt? This is d tau by d a. Now from this expression it will be minus infinity to infinity, t equal to minus infinity, tau is also minus infinity, and t equal to infinity is this also infinity, into del of tau d tau by a, which is equal to 1. Now if we compare this and this, so I can take it as like this: 1 by a delta tau d tau integral minus infinity to infinity is equal to 1. If we compare equation 1 and equation 2, right? Now what is this? Suppose this is 2, this is 3. Now from equation 1, 2 and 3 we can easily tell delta of at nothing but 1 by a into del of t, right? From equations 1, 2 and 3 we have to compare with these 3, right? So if it is del function is scaled by at, the equivalent will be 1 by a delta t, right? Only amplitude will be scaled down, right? Now what is the next property? Is the fourth one. This is like integration property. Fourth one, suppose it is like this: if minus infinity to infinity x of t is multiplied with delta t minus t naught into dt, it is nothing but x of t naught. It's very simple. We know that whenever delta t minus t naught is multiplied with x of t, it will become x of t naught, right? The x of t naught will come outside. So proof is like this: we know that by sampling delta t minus t naught is nothing but x of t naught into, I can make it as delta t minus t naught also. There is no problem. Now here I can replace with that one, x of t naught into delta t minus t naught into dt. So x of t naught will become what? Outside, minus infinity to delta t minus t naught into dt. Now what is the area of this one? If t naught is existing between minus infinity to infinity, this will become x of t naught into 1. So minus infinity to infinity x of t delta t minus t naught x of t naught, and this t naught should be between minus infinity to plus infinity, otherwise it will become 0. Right? Now if I take an example, suppose minus 2 to 0, and this is u of t plus 1 delta t dt. So what is the value of this one? First we need to find what is delta t plus 1. This is minus 1, 0. This is u of t plus 1. What is delta t? Delta t is at here. If I multiply this one, what we should get? U of 0. Yes or no? Now u of 0 means what? So is nothing but 0 at what is the amplitude? 1. Right? So it can be replaced by u of 0 plus 1. So this is the one, right? In place of t naught or x of t naught is here 0. So u of 0 plus 1 is nothing but u of 1. Now if you see, this limit is minus 2 to 0 only, but we got u of 1. So what is this total limit? Minus 2 u of t plus 1 into delta t is equal dt is equal to, you will get 0, because between minus 2 to 0 there is no u of 1, right? So that's why the limit is 0. So one more example we'll see, that is minus infinity to infinity cos t delta t minus t minus 2 is dt. So we know that this is, suppose x of t, and 2 is in between minus infinity to infinity. So we can say directly x of 2. X of 2 is means cos 2 is the value. If I see this one, x of t is nothing but t square, and 3 is between 0 to infinity. So x of 3. and that means 3 square. So 9 is the answer. One more is 0 to 5 sine 2 pi t delta t. Now what is t naught here? So x of 0 value. So sine 2 pi into 0 will get 0. Suppose this problem, if I take one more, if it is like this, minus infinity to 0 t square into delta t minus 3 dt. 3 is not in between these limits, right? So that's why directly the answer is 0, because delta t minus 3 is somewhere here, right? But we are integrating from minus infinity to 0, so there is no common term, so that's why directly answer is 0, right? Next property in integration only, so fifth one, if minus infinity to infinity x of t, suppose this is del dash of t dt is there. So del dash t means del dash of t is nothing but d by dt of delta t, differentiation. So what we will get, minus x of 0, right? One time differentiation we should do, or we can say minus of d by dt of x of 0. Suppose if I integrate double, that is minus infinity to infinity x of t del double dash of t dt, we will get one more time means x double dash of 0. So if I take generalized expression, this from x of t del power n of t dt is equal to minus 1 whole power n into x power n of 0. If we generalized more, that is minus infinity to infinity x of t del power n of t minus t naught dt. So this will become minus 1 whole power n x of x power n of t naught, or we can say minus 1 whole power n d by dt power n of d power n of x of t naught. So this is the differentiation property. If I differentiate one time, we have to differentiate the signal at 0 and minus sign. So d by dt of x of 0. Right? Next one, the last property is sixth one. So sometimes we may get, otherwise we can neglect this also. This is the sixth one. Suppose there is delta of at plus b is there. So how to proceed this one is, take a common, that is t plus b by a. Now a into t, we know this will become 1 by mod a delta of t plus b by a. This is one more property of the del function. If it is a shifting and a scaling at a time. So this is b by a. Now before proceed to the discrete time signals, I am going to discuss one more what you call the property or the functionality. Generally you cannot say property, differentiation and integration of signals. Differentiation and integration of signals. Right? Now how to find this one? So we know if x of t is there, so what is the d by dt of x of t? It can be replaced by x dash of t, etc. Right? Now why we need to discuss this one is, suppose some signal is given like this, 0 to 1 t x of t. How to find the differentiation of this type of signals? So whenever there is a discontinuity, so the differentiation will change. So we have to give the first directions, and this is 1, this is the directions, right? If you see from 0 to 1, it is a constant at 1. When we differentiate constant, we will get 0. But when we differentiate this discontinuity, we will get a value which is the impulse, right? So this impulse is, if I differentiate this one d by dt of x of t, what we will get? At t equal to 0, we'll get one differentiation or one impulse, that is 1, and this is 0, but at 1 we will get, it is downward, right? So downward by 1, so -1 at 1. So this is the differentiation of a signal if it is a discontinuity, right? This is about the integration, differentiation. If what is the integration? Integration is, we can have limits or without limits x of t dt, right? We know if there is a constant, so we'll get t, right? If there is a, suppose integration of t dt, we'll get parabolic, right? Something like this. Next, we know differentiation of t is 1 and integration of 1 is t. So opposite of this differentiation and integration. That means if I integrate this d by dt of x of t, so whenever there is a discontinuity, we will get the constant, right? So that we have to find, right? Or we write some equivalent signals, something like this. If so 1, if I integrate minus infinity to infinity delta t dt, I will get u of t, right? Or if I integrate from 0 to infinity, I will get u of t, because u of t is from minus infinity to infinity. Or if I differentiate u of t, I will get del function, right? Similarly, if I integrate 0 to infinity u of t dt, what is the integration of u of t? We will get a ramp signal r of t, or we can say simply t. Now if I differentiate a ramp signal r of t, I will get unit step signal or unit step function. Remember, when we differentiate the impulse or what you call discontinuity, we will get the impulse. So if I differentiate discontinuity, we will get impulse. So this is an important point when we do the differentiation, right? Similarly, if I said this is, suppose 1 is the delta t, right? Now if I integrate, what we will get? Integration of delta t will get from 0 to 1 like this. So for the previous problem, suppose this is the 0, suppose this is the -1 at t, this is some x of t, right? Now if I integrate x of t, what is the value? We'll see. So from 0 we are getting some impulse of 1 unit step function. Similarly, at 1 there is a -1, right? So again we will get some impulse, what you call unit step from 1, and this is -1. So this is a different signal, right? So that is the 1. And see, this is 1 and this is -1. So what is the resultant you will get? You will get from 0 to 1. So this is the 1. This is a differentiation of this x of t, right? This is one signal and this is one signal. So if I add, this is 0 to 1 1 and 1 to 1, this is 1 and this is -1, both will be cancelled. We will get as 0 to 1, right? So this is about the differentiation integration. Right? Next we will see types of the discrete time signals, right? Discrete time signals. So in this lecture we'll see 1 or 2, then we'll see in the next lecture. The first one is always unit impulse signal, right? Now, or generally we can say this is a discrete, so unit impulse sequence also, right? Sequence. It's very simple. Delta of n is equal to 0 when n is not equal to 0, but it is 1 at n is equal to 0. It's not like in continuous time signals. It is a different sequence, discrete intervals of time. So the notation is like this. This is a 1, 0, and the remaining will get 0, right? Similarly, unit step sequence, that is u of n is equal to 1 when n is greater than or equal to 0, 0 when n is less than 0. So something like this. So impulse, right? Continuation of impulse 0, 1, 2, 3, etc. n, and this is the 1. When n is less than 0, we'll get 0. The third one is unit ramp function or unit ramp sequence. So unit ramp sequence, right? So it is like this. So r of n, or simply I will write x of n, or r of n is equal to n when n is greater than or equal to 0, 0 when n is less than 0. Now see, it will be like this. This is n. When n equal to 0, 0. N is equal to 1, 1. N is equal to 2, 2, and so on. This is 1, this is 2. So x of n is equal to n, or r of n. So this is the unit ramp sequence. In the next lecture we will see exponential signals, periodic signals, right, and some operations on the discrete time signals, then even signal, odd signal, etc. in the next lecture, right?